Consider a robot arm that needs to move to a precise angle, or a wafer stage in a lithography machine, or a drone that must maintain some altitude. Somehow, all of these systems work despite unknown disturbances in their environment and noisy sensor measurements. The purpose of control is to make a system do what you want, despite unknown factors. But how do engineers achieve this? How do you design a controller? Let's find out. In this video series, we'll teach the foundations of control theory that's relevant for motion systems in industry. This series will span 5 chapters: fundamentals, Bode plots, closed-loop transfer functions, Nyquist instability margins, and loop shaping. And in the end, we'll use it all to design a controller and test it out in the real world. Now, admittedly, the field of control theory is huge. And although this series will only cover industry-relevant frequency domain control for stable systems, it'll still serve as a good foundation to learn other parts of control theory as well. The field can be very theoretically heavy, but we'll keep the mathematics as simple as possible. The only prerequisites are complex numbers and a bit of integral calculus. We'll lean less on rigorous proofs and more on examples and intuition. So, let's get started. And one of the best ways I can think of to describe how a feedback controller works in simple terms is with this chicken here. This chicken here is somehow desiring to keep its head stationary, even though I'm moving it side to side with my hands. This is referred to as disturbance rejection. If I give a disturbance to this chicken, its head remains exactly where you'd expect it to be, just perfectly still. How does the chicken do this? Okay, well, let's try and figure out how this works. Let's make a very simplified model. Let this box here denote the chicken's brain. The brain somehow decides on just the right voltage to send the neck muscles such that its head will be at its desired place. I'll call this voltage signal U of t. The muscles input this voltage, contract, and output a force in newtons on the head of the chicken. The head feels this force and moves, in meters, accordingly under Newton's law of motion. But that's not all. The chicken also has eyes which can sense where the head position is, also in meters. We'll call this measured output head position Y of t. And the best thing about having a sensor is that it can feed that information back and compare Y of t with the desired head position, which I'll call the reference, R of t. This summation block literally just subtracts these two signals. In an ideal world, the difference between these two signals, R minus Y, should be 0. But in reality, there will always be some measured error, which I'll call E of t. The brain will then input this error signal and will generate a new voltage output, and the same process happens again, over and over and over again. This biological analogy is useful because it closely resembles the feedback diagrams engineers use to design digital controllers for mechatronic systems. The brain acts as a feedback controller, and the muscles are the actuators that push or pull. The head is the mechanism being moved, and the eyes are the sensors providing measurements. Now, to simplify things further, let's combine everything that's not the feedback controller into one giant block, which is called the plant. The plant is usually denoted with a capital G, and the feedback controller with a capital C. Now, in almost all motion systems, there's not just a feedback controller, but also a feed-forward controller, which I'll call CFF. The feed-forward controller doesn't use the sensor information. It only looks ahead. As you can see, if I just show the feed-forward part in isolation, it anticipates the control action needed based solely on the desired outcome, R of t, without waiting to see the result, Y of t. Okay, let's go back to the full diagram. Now, in this series, we're going to simplify things and only focus on the closed loop. Not because feed-forward controllers aren't important, they do the vast majority of work needed, but because it turns out we can design these two controllers independently. But what rules really govern this abstract diagram, and how can we use it to find out the feedback controller C? Well, let's build some intuition by zooming into one part of this diagram and only considering the plant G, which is an input U and output Y. The most simple example I can think of for this plant G is a mass m free to move around on a frictionless surface with some displacement y of t, and being pushed by an external force u of t. Note that in this example, the force u of t is the input, and the displacement of the block is the output y of t. And the plant is the whole system that relates these two. From Newton's laws, we know that this system is governed by the equation my double dot of t is equal to u of t. This is a differential equation which can be solved using what's called a convolution. U of t convolved with g of t is equal to y of t. This star here stands for the convolution, and this little g here is the impulse response. It's what the output would be if we were to give the mass a quick whack with a hammer. In other words, if we set u of t to be this delta spike here, then whatever the output looks like will be the impulse response, g of t. And it's worth noting that different systems have different impulse responses. This system here, once tapped with an impact hammer, has an impulse response that looks like this. And so you can really think of the impulse response as something that contains key information about your system. I'll cover what an impulse really is and how to calculate the convolution integral and the intuition behind it in another video. But for now, I want to focus on the big picture. We now have a more mathematically precise understanding of our block diagram. We can now describe the plant as the convolution of the impulse response, little g. This works because u convolved with g equals y. And by using the exact same logic, we can make the following adjustments for the entire closed loop. And great, we're one step closer to designing the feedback controller. But there's a problem. Designing a controller using convolution integrals is a complete nightmare. The operations are very complex, and there's very little intuition to help guide us. We need a better way. Fortunately, a French polymath in the late 18th century had developed a mathematical technique that transformed our understanding of differential equations. Pierre-Simon Laplace came up with what is now known as the Laplace Transform, often written with a fancy L like this. And it converts some function of time, say x of t, into another function of a different variable, capital X of s. The way it does this is by calculating the integral of x of t times e to the power of minus st dt from time equals 0 to infinity. Now, if you're seeing this for the first time, this must seem completely arbitrary to you. Rest assured, I'll make another video that goes much deeper into the caveats of this operation and attempt to give an intuitive explanation as to what this complex variable s really means. But for now, it suffices to know that we can go from the time domain t to the s domain by applying the Laplace transform L. And it turns out that there are a few useful properties of the Laplace transform with regards to derivatives. Firstly, it turns out that the Laplace transform of a derivative, x dot of t, is just equal to s times capital X of s. And the Laplace transform of the double derivative, x double dot of t, is just equal to s squared times capital X of s. This is a useful property because this operation replaces a complicated derivative with a relatively simple multiplication of s. Okay, but how does this help us with convolutions? Earlier we had written that y of t is equal to g of t convolved with u of t. And it turns out that if you Laplace transform both sides of this equation, then you will get capital Y of s is equal to capital G of s times capital U of s, where big Y, G, and U are the Laplace transforms of little y, g, and u respectively. This is pretty remarkable because it simplifies a very messy convolution in the time domain into a fairly simple multiplication in the S domain. And to help build some intuition behind this subject, I thought I'd introduce this analogy of a Rubik's Cube. Let's say we have some input u of t, and we seek to find some output y of t, but to do so we need to solve the convolution integral, which is generally quite hard, and something I'm trying to symbolize with solving this Rubik's Cube. Now instead of doing this, I'm going to Laplace transform just here. And once I Laplace transform, what I get is no longer a Rubik's Cube to solve. I get an entirely different puzzle in the S domain. The Laplace transform of u of t is just u of s. And now in order to get y of s, our output in the S domain, I no longer need to take a convolution, I just need to do a nice, easy multiplication, which is what I'm symbolizing with this puzzle just here. And this puzzle is actually much easier to solve. Let me just see if I can quickly do it. There we go, much more easy to solve. But in the S domain, this is still unrecognizable to us. So let's inverse Laplace transform to get back to the time domain. And so if I take this inverse Laplace transform, what I get is a perfectly solved Rubik's Cube, implying that I've managed to find y of t without ever needing to calculate this convolution integral just here. I hope this example wasn't too patronizing. Okay, so let's see if we can use this new technique to help us design our controller C. Well, if we Laplace transform every equation that makes up this feedback loop, then we get a Laplace transform of our reference, R of s here, and a Laplace transform of our measured error, E of s here, U of s here, and Y of s here. But most importantly, we also have a multiplication of capital C of s here, and a multiplication with G of s here. And already this looks so much nicer. I mean, our controller is now a function of s that relates the input error, E of s, to the output U of s through the relation C of s times E of s equals U of s. Likewise, our plant converts the input U of s into the output Y of s through this relation. From now on, I'll refer to blocks like these as transfer functions, because they transfer an input to an output via functions like C of s or G of s. A good way to remember it is output divided by input. Also, to make the diagram a bit more aesthetically simpler, I'm going to omit the multiplication sign from now on, since it's implied. Okay, so let's see if we can simplify this feedback loop. Now that we're dealing with multiplication, we can combine these two blocks together into just one transfer function, which I'll call capital L of s. This new block is called the open loop transfer function, because it's what relates r to y if the feedback path was removed. In other words, with the loop open. But what about the loop closed? Is it possible to get some transfer function that relates the reference r to the output y in this case? Let's do some math. Well, we know one equation is L of s times E of s equals y of s. And we can get another equation with this summation node. R of s minus y of s is equal to E of s. If we substitute out E of s from equation 2 into equation 1, we get L times r minus y is equal to y. And if we bring the y's to one side, we get LR equals y plus ly, which means that we get this, and this, and this. And there we have it. We have our transfer function, which I'll call T of s, which relates the output y of s to our input r of s. And since L is equal to G times C, then T is equal to GC divided by 1 plus GC. And take a moment to appreciate just how important this is. We've got one transfer function that encapsulates everything in this closed loop. This means if we design our controller to get the properties of T of s to be just right, then maybe we can get our output close to our reference, which is what we want. But how do we do this? And what properties do we care about? Well, let's start by building some intuition by considering once again a mass m with an output displacement y of t and an input servo force u of t. Newton's law states that my double dot of t is equal to u of t. And if we Laplace transform both sides, then we get ms squared times capital Y of s is equal to capital U of s, which means that our plant g is just y divided by u, which is equal to 1 divided by ms squared. And now let's say we want this mass to follow a reference, which I'm going to visualize as this shaded mass with displacement r of t. What possible control law, u of t, could we choose to match this reference? Take a moment to think of one. Perhaps you think u of t should be proportional to the error, where this p here is a constant called the proportional, or p gain. Intuitively, this feels like it should work because this control law is analogous to a spring force. After all, if y is greater than r, then the error will be negative, and the force will push it back to the left. Likewise, if y is less than r, then E will be positive and the force will push it forward to the right. Well, let's try it out. Laplace transforming, we get u of s is equal to p times E of s. So our controller is c is equal to u divided by E, which is equal to p. That means, for this example, we have a feedback loop where c is equal to p and g is equal to 1 divided by ms squared. And now recall that the closed loop transfer function t was just gc divided by 1 plus gc, which in this case turns into this and this. And what that means is that all of this gets squished into this simple expression. And the result here is actually solvable. We can simulate what this looks like for any given reference using a computer. This is some MATLAB code that simulates the output given a step reference. The result is a plot that looks like this, where r of t is a step. It's 0 for all negative time and 1 for all positive time. And y of t is this corresponding curve. Now, this does not look good. We'd ideally like our output to match our reference, and that's not what we're seeing here. Our reference has a step, which means it moves suddenly to the right, and our controller recognizes this sudden error and applies a large force pushing it right, but it overshoots. The controller compensates, pushing it left, but because the block has inertia, it overshoots again. And on it goes, oscillating forever. Clearly, we haven't designed a good controller here. Let's try using our mechanical intuition again and see if we can design a better controller law for this system. How about instead of creating a controller that mimics an ideal spring, we get a controller that mimics a spring and damper? A damper resists velocity, so our new control law we're designing will be u of t is equal to p times E of t plus d times E dot of t, where d is called the derivative gain. Going through the exact processes before, we get u of s is equal to p times E of s plus d times s times E of s. And so our controller is c of s is equal to p plus sd. Now we can calculate the closed loop transfer function t of s. Simulating a step response once more, we get this. And it looks much better. The derivative gain resists velocity, not displacements. So when the mass moves to the left, the damping force component acts to the right, helping to prevent overshoot and settle the system. The time domain plot looks like this, and as you can easily see, the derivative gain really helps to prevent these oscillations. And wonderful! We've now designed a controller, called a PD controller, that seems to work quite well. One tempting approach from here is to tune these values of P and D until we get a response that has the desired performance metrics, like rise time, overshoot, and settling time. This method is called time domain tuning, and techniques like this are commonly used in the process industry and for power distribution networks. And one thing you'll notice by playing around with these values is that very large values of P and D result in fantastic reference tracking. And what's interesting is that this is actually no coincidence. Remember, our feedback loop looks like this, and the open loop transfer function is this, and the closed loop transfer function is this. If our controller becomes very large, say infinity, then L also approaches infinity. This means t will become infinity divided by 1 plus infinity. Now, admittedly, the plus 1 here doesn't do much anymore, so t will approach 1, which means that y will approach r. We've got perfect reference tracking. This simple concept has a name, high-gain feedback, and it's a fundamental principle when designing controllers. Hey, and so it seems like we're completely done. We've designed a controller that can work incredibly well. Let's copy and paste this controller for every plant that we come across, and it'll work, right? Well, not so fast. While PD controllers are great and commonly used in many industrial applications, they can't do everything. Consider this plant here, which is a simple model of the altitude of a Boeing 747 airplane. If I use the same controller for this plant, then look at what happens to this step response. Oh wow, it is completely unstable. The key takeaway here is that there is no universal controller. A custom controller needs to be designed for every plant. And so whilst we've made a lot of progress so far, we still have a bit more to go. And to help guide us in our quest to design a controller, we'll need to squeeze out some insights from this mysterious closed-loop transfer function. In particular, we need an easy way to tell whether a given controller will lead to a stable system or not. Does such a method exist? Well, yes, and we'll talk about that next time. Thanks for watching.